In section 4.4, we're actually going to go completely through the entire regression analysis. So the steps that we've learned for this chapter, the first thing you should do is you should summarize the data graphically by constructing a scatter plot. Now, based on the scatter plot, decide if it looks like a relationship between x and y is approximately linear. Only if it's approximately linear should you proceed to the next steps. The third thing you should do is find the equation of that least squares regression line. After that, you should construct a residual plot so that you can look for any patterns or unusual features that may indicate that a line is not the best way to summarize the relationship between x and y. If you don't see any pattern, then you can keep going. Then you would calculate the value of the standard error, SE, and R squared, and interpret them in context. The standard deviation is going to describe the deviation from the y values to the line, and R squared is going to tell you the percent of the variation that's explained by the regression line. Once you have the values for the standard deviation and R squared, then you decide if the least squares regression line is useful. You need a small standard deviation value and a large R squared value. Now, these are small and large with respect to the data itself. If you're dealing with data that's really, really small, then that makes your criteria really, really small for your small standard error. If your numbers are quite large, then you can have a little more leeway there with what makes a small standard deviation. If all of those steps are completed, then you can use the regression line to make any predictions. So let's use example 4.15 in order to walk all the way through these steps where we aren't using the technology. So this one's going to give us most of the things that we need, and we're going to go through the process. So this is the data from the beginning of this chapter, looking at this model that looked at a blood test to predict the age of the crime victim. So you have a scatter plot. What do you see? I want to know the strength, and that looks like a pretty strong relationship. If it was weak, it would be scattered all over the place, and if it was moderate, it would not quite fit so nicely in a vertical, or not vertical, in a diagonal bar there. So this is a strong, and it is linear, and it is negative. So I'm looking for strong, moderate, weak, linear or curved, and then negative or positive. We're told that the coefficient, or correlation coefficient, is negative 0.92. That's what we suspected looking at the scatter plot, that it was going to be a strong relationship, and that's exactly what we have determined. It tells us that it's strong and negative relationship. We're given the equation of the least squares regression line, y hat equals negative 33.65 minus 6.74x. The residual plot showed a few observations with large residuals, but they weren't judged to be influential, so we didn't have any other unusual patterns. So that means that we can keep going in our analysis. We can get the standard deviation and R squared, and in this case, the standard deviation of 8.9, these are years. You would have to decide if that is small enough for you. Are you okay with making a prediction within 9 years of somebody's age? It's not a fantastic value, but it's certainly not an extremely large value compared to ages. Let's start with R squared. What does that tell us? Well, if we multiply by 100, that tells us the percent 83.5. That's the percent of the variation in y. That's explained by the least squares regression line. That's pretty good. You can think of R squared values as test scores. If you got an 83.5 on a test, you knew the material pretty well. And least squares regression line is really long, so I usually write LSRL. And then our standard deviation E, and that tells us that a typical difference between the actual age and the predicted age is about 9 years. Now, 9 years is somewhat of a large value, but it still would get you narrowed down to an approximate decade of age, which is not too bad. So for question 6, I would say that this is a relatively small standard error, standard deviation, and a large R squared. And so the least squares regression line is useful for predictions. And so finally, since we have determined that it is useful, then let's look at an example of making a prediction. If the blood test is measured to be -10, what's the predicted age? So we'll get our y hat by substituting into this equation -33.65 minus 6.74, and then multiply that by 10. Depending on the calculator you're using, will determine if you can do this all in one step. Most scientific calculators can handle all of this done at once. So if you type -33.65 minus 6.74 times -10, you should get 33.75, which is about 35 years old. Now, here we do recognize that the standard deviation was 9 years, so we would not be surprised if we found that the age was actually somewhere between 25 and 43. Now I want us to do a example where we're using StatCrunch. So I will be posting this data in Canvas so that you can download and follow along with us. First, we'll need to load the data set. So it's available in Canvas under the Chapter 4 Learning videos. And when you click From File on my computer, you just need to find where you've saved that file. And you can see here where I have all of the data sets, so if you're ever in need of one, I have them. They might be available somewhere in WebAssign, but I have not found them yet. So we upload our data. The only problem with the data in WebAssign, it is randomized. So when you have a randomized problem, a lot of times I cannot get the actual numbers that you have in there. So one thing that you can do is you can usually copy and paste the data, but it's a whole process sometimes to get that data in there. Sometimes it's easier just to type it in. So this data set is looking at lobsters, and the question is, can you tell how old a lobster is by its size? So here, even though age is listed first, the explanatory variable is actually this carapace length, which is the size of part of the lobster. So when we go to do stat regression simple linear, we need to select that length for X and the age for Y. It is important that you know what you're trying to predict. Now, we want to get our fitted line plot and our residual versus X values. We will need that. So hit either Shift or the Command key. And we're not going to be looking at the actual residuals and predicted values, so we don't have to save those unless you want to. When you click Compute, you have all of this information for us. So we have the regression line. The equation is given right here. We know R, we know R squared. We have our standard deviation estimate. If you wanted to get the intercept and slope from the table, it's right there. So everything that we need is available from this first screen. We can look at our scatter plot at the second screen, and here we see that it is a strong, positive, linear relationship. And this regression or this residual plot looks okay. My concern is that it's close together here on the left, but it gets really wide on the right. What that tells us is that for small lobsters, this model is really good, but for larger lobsters, this model isn't so great. That makes sense because as a lobster's growing, then you're going to be able to figure out about how old it is. But at some point, the lobster won't grow quite as quickly, and so that's why the model seems to fall apart. So you would use some caution here simply because the regression or the residuals start to get really big towards the end. But I think we're okay. There's no like strong curve or anything. So we will keep going, but that is something that you should consider. So all of the things that you would need in order to go through this linear regression analysis is right here. The scatter plot is strong, positive, linear. And so we can get the equation, and that is that the age is equal to negative 1.076. I'm going to go ahead and round. 3 decimal places is usually enough, plus 0.029, and then the length. We looked at the residual plot, and we saw that it's not perfect. It does kind of trump it out, but it's okay. Then we can get our standard deviation, 0.299. That's relatively small compared to the values in the data set. And we get an R-squared of 0.8879. That tells us that 88.8% of the variation in the ages can be explained by the regression line. So that's a really good value. And so between a small-ish standard deviation and a large R-squared, then the regression line is helpful for making predictions. And so finally, if we wanted to make a prediction for a lobster with a carapace length of 127.5 millimeters, then we need to substitute that 127.5 into the equation. So here you can see where I took that equation, rounded to 3 decimal places, and replaced the length with the given length. And so that tells me that I can predict the age of this lobster to be about 2.62 years old. I do want to show you a trick that you can use in StatCrunch when you're doing these predictions. So if you go to Option Edit, you can actually make a prediction right here. And you can say my X value is 127.5. Now you can only do this one value at a time, but you can put that X value right there. And when you compute, you are going to get your predicted Y right there. And the only reason that's a little different from what I got is StatCrunch is not rounding, so they are using every digit right here. And so if you're doing this in WebAssign, the programming may or may not accept the answer. So if you're not getting the right answer, you might have to do it by hand. But that is a way that you can get this predicted Y. We'll learn about these last two things at the very end of this class, so don't worry about it right now. But if you're curious, it's just giving us a range of values that we are confident that the true age of the lobster would fall between.